This is example 15.2 from Discovering Design with Chemistry. A chemist does an experiment with the following reaction, and it gives the reaction. He runs 3 separate trials of the reaction, varying the concentration and measuring the instantaneous rate. His results are tabulated below. What is the rate equation, including the rate constant, for this reaction? So again, we want this rate constant right here, this K, and we're given the rate that happened with each of those different concentrations that happened. So let's just start by using the rate formula, which is this right here. So we're given the rate for the first one. So this is trial number 1. That's 0.00243 M per S. I got that from right here. That's equal to our rate constant, which we don't know. The molarity of the first thing, this is going to be our A column, and this is going to be our B column, which means our X for this one and our Y for this one, we don't know yet, but we're going to figure it out. Remember, for this stuff, it's not the, it's the reaction order. It's not like a coefficient or anything like that that gets that exponent for us. All right, so 0.30 M to the X, which we don't know yet, and then B is 0.30 M to the Y, and those two numbers came from this first row, which gives the concentrations for hydrogen gas and the concentration for the NO. All right, so let's move on to the second one. That's as far as we can get with that one. We're just going to line up our 3 rate equations, filling in the pieces we know, and then we'll come back and get it done. All right, so 1 is done. We're moving on to number 2, and I'm just filling in the rate, leaving the K as is, and I'm going to fill out the molarities of each. So 0. Here's the concentration of this one. Oh, I forgot my M. Just squeeze it in there. And then my concentration of this one, again with a Y. And then my third one. In the book they do 2, and then they do something with the first 2, but I'm going to go ahead and put all 3 rate equations on there so that we can work from there and see what's happening. I'll explain in a second. We're just going to get them all lined up. And I'm using different colors so we can kind of keep straight. On the bottom row, we finally have a different concentration for H2. And then NO is different. Okay, so if you look at these 3, we have 3 different equations. They all have the same K, the same X, and the same Y. So by putting them together in some way, we can figure out what that missing variable is, but we can't have too many variables at the same time. If you go back and think about algebra and how sometimes you'll have like y equals 3x plus 5, and another one that's like y equals negative 3x minus 6, and we want to figure out where those 2 lines intersect on a graph. We're trying to figure out the solution that for x and y that will fit in both. We do this little fancy thing where we take one and we subtract it from the other, or we add it to the other depending on what it is. And so in this case we would end up with canceling out this middle, because 3x minus 3x, and we could solve for that to find y, and then we could plug that in and solve for that to find x. We're going to do something similar here, because we're also trying to find a k and an x and a y. The k is the same in all 3 equations, the x is the same in all 3 equations, and the y is the same in all 3 equations. But we can't just line them up and subtract them, because nothing's being added or subtracting here. Everything here is being multiplied, or if we move it around, it would be divided. So what we're going to do is we're going to do a similar thing where we take 2 of the equations that came from 2 different trials, and we're going to divide one by the other. So I'm going to start with the first 2, and I'm going to divide, oops, thought I had my marker up. We're going to divide one by the other. Because I want to have a nice non-fractional number on the left, I'm going to put number 2 on top. So I'm going to put 0.00972 M per S equals, and I'm literally just copying this, so let me be quiet for a minute. All right, and now put a different color line. I'm going to do the same thing, but I'm going to do the first one. So this is the first equation, just as it's written up there at the top of the screen. All right, I'm going to use my eraser because I'm actually splitting these into into two different formulas. I'm going to put an equal sign between them. All right, so on the left, if you notice, these units are going to cancel with these units, and we just have something to divide. On the right, we have a k here and a k here. Those will cancel. This 0.3 m to the x is the same as this one, which means that also cancels. So let's take out our calculator. Oops. Let's take out our calculator, and we're going to go ahead and divide 0.00972 divided by 0.00243. All right, so on the left we get 4, and let's go ahead and write it with the right number of significant digits, which is 3. So 4.00, and there's no units because we canceled those. And then over here we can take this section right here, this left, and if you've ever done fractions where you have 2 over 3 and it's maybe put to the second power, you can change that to 2 squared over 3 squared. You can do the same thing going backwards, going this way, and so that's what we're going to do. We're going to take this and put 0.60 m over, well, yeah, over 0.30 m, and then raise the whole thing to the power of y. These units will cancel, and you can probably see what 0.6 divided by 0.3 is. If I multiply the top and bottom of that fraction, I would have 6 over 3, so I'm going to have 2 on that side. I have 2 significant digits, so that would be 2.0 to the y. So let's look at this real quick. We have essentially, I'm going to simplify it and then add back in. I have 4 equals 2 to the y. What could y be? 2 to the what is 4? Let's put our stuff back. Y equals 2. So now we have the rate order for B. All right, so we can do the same thing to find X. So let's take 2 of them. In this case, we got rid of the X's, or we got rid of the molarities that were raised to the X power because they were the same, which is right here. So to do the same thing to find the Y's, to find the X, we need to get rid of the Y. So we need to find 2 Y's that are the same. So this one and this one are the same. So we're going to take this next set of equations and we're going to use trial 1 and trial 3 so that we can compare. So using trial 1 and trial 3, which one is bigger? Let's not all over. Which one is bigger on the left? The single number that we're working with, it's not a whole bunch of stuff together. That's number 3. So let's put that one on the top. So 0.00486 m per s equals, you know what? Why am I doing this in purple? Let's do this in the right color so we don't get confused. 0.00486 m per s. And then on the other side we'll have k 0.60 m to the x, 0.30 m to the y, and then I will use purple to make my fraction bars. And then remember we're using trial 1 because trial 1 will get rid of one of our coordinates. All right, let me pull out my purple. All right, so units cancel, the k's cancel, this cancels, which is of course how we designed it. So moving down, we're going to divide these two. You can probably look at those numbers on the left and see what they divide, but for the sake of those who do not like to just do math in their head, 6 divided by 0.00243. There's a 2. Let's keep significant figures the way we know how to do. So that'll be 3 significant figures. So we'll do it like that. And then the other side, you can probably also see you've essentially got 60 over 30. So that side's also going to be 2. But let's type it in anyway. So 0.6 divided by 0.3, 2. And because this side has 2 significant digits, we're going to keep 2 significant digits. Actually, before I write that, let me point out what I did here. It's probably, you can probably tell, but again, I took my numbers, combined them in one fraction, and then raised that whole fraction to the x, which gave me 2. But I'm going to write 2.0 because we have 2 significant figures on the top and 2 on the bottom. And if you think about this without those significant figures, 2 equals 2 to the x, what must x be? X must be 1. So x equals 1. So now we have the reaction order for each of the different reactants in this thing. So we've got a lot of what we need to move forward. Okay, so now that we've got those pieces, we just have, let's look at our equation real quick. Slide this aside. So here's our rate equation. We have rate equals K A X B Y. What do we have? Well, we have 3 different rates, so we're good there. We're looking for the K still. We have 3 different A's to work with, 3 different B's to work with. We have an X and a Y. And so to do this, to find the K, we just need to plug something in for literally everything else, and the K will be the only thing left. For this one, it does not matter which rate equation you solved. He used the one from trial 1, so in case you're following along with the book, I will also use the one from trial 1. So we put in the rate that we were given. This is the rate for the reaction for that specific concentration. We don't know the K. That's our mystery. We're going to put in the molarity for H2, 0.30 m, and our X is 1. And then we're going to put our molarity in for the NO, which for trial 1 is 0.030 m, and Y, our order for this one was 2. Let's rearrange. We're going to say K equals 0.00243 m per s, and these 2 numbers that are over here are going to go to the other side and get divided underneath here. So I'm going to just use parentheses. All right, so let's type all these numbers in the calculator. All right, we're going to put the calculator over here so it's out of the way. So 0.00243 divided by, let's put this in parentheses, 0.3 times, I'm going to put the next one in parentheses, 0.3 to the second. I could have simplified that, but I'm not going to right now. All right, so we get 0.09. How many significant figures do we need? We have 3, and on the bottom 2 and 2, so we need to keep 2 significant figures. These zeros in front of the 9 do not count, so we need to put another 0 after the 9. So 0.09 and then one more 0. And what is our unit? We have an m here that will cross out with an m here. We have no more m's to cross out, and this m is squared, so 1 over m squared times s. So that's our unit. I was about to circle that, but actually let me not, because what they actually asked for was the rate equation, including the rate constant. This is our rate constant. That's what the K is. So now we can actually build the rate equation. We have the rate equation, the rate constant, and we have the orders for X and the orders for Y. All right, let's pick a totally different color so it doesn't conflict with anything else. So our rate equation is going to be rate, because that changes based on the concentration, equals, the K is the thing that we just figured out, 0.1 per m squared s, and then the concentration of, oh, you know what, let's not just write 8, let's write the concentration of H2, and that one's raised to X, which is 1, and then the concentration of NO, and that's raised to 2. So there is our final rate equation, and that's the answer to the question. So to do the rate equation, including the rate constant, we had to find all of those pieces. The rate constant needed to wait till the end because we had to be able to plug in all the other numbers. So we had to find the X and the Y first. And to find the X and the Y, the trick we used, or the method that we used, was we found things that would cancel. We found a way to cancel everything by dividing. If you have more questions on this, I can answer them better in person, I think.